Okay, good morning.
Someone was meant to share something.
My mic is upside down. Okay? Thanks. So yesterday I gave you a sketch of the definition of chiral conformal field theory a la Siegel. Here's again that same sketch in a slightly more organized fashion. Like these are the main things that I think one should remember. And I have prepared a handout that you should all have a copy of. If someone is missing it, please let me know and I will. So this handout is organized in the same way that this chart is organized. Namely, there's these labels 1A, 1B, 2A, 2B, 3A, 3B, which spell out the things that, well, I mean, for example, yesterday I said the assignment of a certain linear category to every one manifold is symmetric monoidal. Well, maybe you know what it means and you're able to write it down on your own. But it's also written in this handout, and you can double check that whatever you're writing actually agrees with what is there and that you haven't forgotten some of the, I mean, any given one of these coherences is like, oh yeah, that's okay. But like just making sure that you have them all sometimes, I think that can be a bit tricky. Anyway, so it's spelled out. One other thing that I mentioned yesterday, and I didn't have time to elaborate, I just want to come back to it, is the notion of infinitesimal equivalence between two such things. Suppose I have two chiral conformal field theories as described here, and that there's a map between the transformation from one to the other. So here's a way in which the transformation can be very close to being the identity. You could have a thing that is an isomorphism as far as all this first column is concerned. Like the category that you get and the functors and these things just are the same for one of the CFTs and for the other CFTs. And then here, the things, well, what do we have? For every object of this category, we're going to have a vector space. If I have a map between CFTs, I'm going to have some linear maps between these vector spaces. And suppose that these linear maps are dense embeddings, like one vector space maps into the other vector. These are topological vector spaces in a way which is just dense. Should think of like, say, the inclusion of smooth functions into L2 functions. I mean, I can talk about a representation of a group on the space of smooth functions on a manifold, or representation of a group on the set of L2 functions. These things are commonly called infinitesimally equivalent. It sort of doesn't really matter, like they're not the same, but they should be treated as the same. And you have a similar thing here. So that's a thing that can happen, and yeah, that's why I phrased the conjectured equivalence yesterday between, say, vertex algebras and chiral conformal field theories as being not quite an equivalence, but an equivalence between these things up to this notion of infinitesimal equivalence. Great, so that's all I wanted to say. Great, there is one thing that I didn't have time to talk about at all last time, yesterday, and which I want to devote this lecture to, which is what is this beast, which is denoted here like that. So what is this? If I fix a circle S, so just a one manifold which is connected and has diffeomorphic to a circle, by an S, annuli with boundary parameterized by S, I mean the set of, so an annulus is something that I have already drawn. Let me draw it again. You have it's a complex subordinate with no topology in between. So genus 0, the inclusion of one boundary into the whole thing is a homotopy equivalence. And when I say that, and when I write with respect to S, so S is a fixed one manifold, I'm going to mean that I have a fixed isomorphism between S and the incoming, so this is the analyst, I call it A. So a fixed isomorphism between S and the incoming boundary, and also a fixed isomorphism between S and the outgoing boundary. So it's the same one manifold that parameterizes both sides. And why is that important? Because then you can compose these things. I have one of those, another one, then you can compose them because all these boundaries are, you know how to identify them. So the collection of all these things, or more specifically, the collection of equivalence classes of these things up to biholomorphic isomorphism, like your obvious notion of isomorphism, that forms a semi-group, which I denote S is the semi-group of annuli with boundaries parametrized by S. And what do I mean by this? I mean, that's not the semi-group, it's a central extension of the semi-group. It's another semi-group that admits a map to this semi-group. And the kernel of the central extension, namely the center, which is this thing, is a group isomorphic to C star cross Z. The Z is easy to describe. The Z is, this case here is homotopy equivalent to S1. So let me describe a semi-group. Actually, it's going to be a subgroup that is going to make it obvious. So first of all, I can look at those annuli where the blue and the red just touch each other and there's no bulk. That's allowed. And that is, if you think about it, I'm going to have an abstract circle and then two maps, one from S to that thing and one from S. You can take the composite, and that's going to give you a diffeomorphism of S. So the group of diffeomorphisms of S sits as a subgroup of that. More precisely, orientation-preserving diffeomorphisms. And if I pick an identification of S with a standard circle, I have a further subgroup, which is just a group of rigid rotations. So there's a group isomorphic to S1 that sits inside here, just rotations. And it turns out that that inclusion of rotations inside this, inside that, all these are homotopy equivalences. And in particular, one can take the universal cover of either rotations, that's going to be R, or this thing, or that, and that accounts for the existence of this Z in here. That's taking the universal cover. And then there's a more subtle other term in this center, which is isomorphic to C star, and that's what I want to talk about right now more in detail. So one fundamental insight, which is due, I believe, independently to Graham Siegel and to Yuri Neretin, is that even though this thing is not a group, I mean, obviously, as soon as an analyst has some bulk, there's no way of gluing some more analysts so that I get the thing with no bulk. So it's a semi-group, it's not a group. Even though it's not a semi-group, it behaves very much like a group. Specifically, it behaves as if it was the complexification of this thing, which is a group. So the complexification of this can be proven to not exist. There does not exist a Lie group. There does not exist an infinite dimensional Lie group, because Lie algebra is the complexification of this thing here. So maybe I should write down what the Lie algebra of diff S is. The Lie algebra of that is the algebra of vector fields, which I will denote like that, vector fields on S. So if you think about what is an infinitesimal diffeomorphism, you rotate your circle a tiny bit or maybe stretch it a bit, Each point is going to go to an infinitesimally close point that determines a tangent vector at each point. And so that's a perfectly good Lie algebra. I put to the Lie bracket of vector fields. And it's a Lie algebra over the field of real numbers because that's a real manifold. And you can take the complexification of that Lie algebra. That's now a Lie algebra over the complex numbers. And you can ask the question, is there a Lie group whose Lie algebra is the complexification of this thing? And turns out that it can be proven. The answer is no, that does not exist such a thing. But the claim is that this, to some extent, behaves like a sub-semi-group in this non-existent Lie group, which would be the complexification of that. So how would one go about arguing why is this a good candidate for complexification? Well, the first thing that you might want to do is to compute the tangent space of this thing at some, maybe at the identity, maybe at any element, and see that you get the complexification of that. So here's a tangent space at the point A to this manifold. Well, it's not quite a manifold. It's a manifold with boundary. So the way to make sense of that is really to realize this as a closed subset of some thing that does have a tangent space, and to compute the tangent space of that ambient thing, like or rather I should say closure of some open subset. I think that. Anyways, tangent space is isomorphic to, so here's what it is. It is vector fields on okay, so what is that? This is the set of vector fields that are just supported on this blue manifold, which can be either parallel to the blue manifold or pointing inwards or maybe outwards. If you think about it, the tangent space to A at any given point is canonically the complexification of the tangent space to S, to this blue manifold, because this ambient thing is complex and this is a real submanifold. And so I can say tangent, this is the same thing as just complexified vector fields. So I have one of those, and then one of those here. And intuitively, if you have one of these here and one of these here, it tells you how to modify the whole picture a bit. I can push this blue thing, and then it goes a little bit further out and further out. And now I have an infinitesimally close annulus. And the only thing you need to worry about is that maybe I've just reconstructed the very same annulus. Suppose that this was a completely straight cylinder. And suppose that this vector field was just completely straight, point to the right, and that one also was completely straight, point to the right, and it's telling me, take this circle and move it a bit to the right, and take this one and move it a bit to the right, and guess what? We haven't really changed anything. We've just translated the picture. So you need to account for the fact that maybe you're not changing the isomorphism class. You're just translating the whole thing. And, well, how do you know that something is not changing? Well, this translation extends to the whole bulk. It's like a thing that exists everywhere, just like translation everywhere. And whenever that happens, you haven't changed anything. So this is the vector fields that are defined everywhere in the bulk and that they don't change the. So let me try to give you something which is a little bit more like a proof for this. Proof. Any analysis A can be embedded in P1. So how do I embed it in P1? See P1 in the two-sphere. Take your annulus, glue in a disk on one side, glue in a disk on the other side. Then you have a Riemann surface of genus 0, and then you invoke the classification of Riemann surfaces of genus 0. The so-called Riemann uniformization theorem tells you that there's only one isomorphism. So you pick an isomorphism to P1. And then the restriction of that isomorphism to A is going to be the embedding, which I claimed exists. So you pick such a thing, and then now I'm going to write down a manifold in which this thing embeds somehow. So M is going to be the set of pairs of maps from this circle that I have fixed to P1. I'm not going to take all maps. I only want to take the maps that look like that. So if I take, here's my P1. I'm going to take maps that, so gamma in is going to be for the incoming, gamma out is going to be for the outgoing. I want to have two maps that define an annulus, that such that maybe they are allowed to touch a little bit, but so I want them to be in such a way that there exists a thing in between. Of course, if they cross, then that's not going to be allowed. So that's going to be A, which is embedded.
Sorry, did you want it to model complex structure like half plane at the boundary? So how can you touch two boundaries?
So each of these curves is embedded, and well, the easiest situation is when they're disjoint. That's certainly allowed. And then you need to make sure that the orientations are right, that somehow they are, the red one is to the right of the blue one, but also limit situations where they touch for a little bit is allowed. Things that are infinitesimally close to a situation where they're disjoint are the things which are allowed.
So you just touch at one point? Or?
Possibly a whole interval, possibly you touch at, you're allowed to touch. What's important is that the, maybe I should write it like that. The area to the left of gamma in and right of gamma out is an annulus as defined earlier, namely a thing that looks like that. Okay. This area in between is what you want it to be. Then any such things define an annulus, essentially by definition. I told you only look at those that do define an annulus. And so we have a map from M to annuli that sends gamma in, gamma out to the A, the area, call that A. Well, here it is, A. And I will be interested in the fiber of this map, namely the pre-image of a given A And the map, the fiber of this map is the set of possible embeddings of A. So that's the same thing as embeddings A into P1. That's what this fiber is. And then we look at this thing, and at the level of tangent spaces, I'm going to write here, what do we have? We have the tangent space at this pair gamma gamma of M, mapping to the tangent space at A of annuli. That's surjective because every annulus can be represented by one of these. And the kernel is the tangent space to the space of all embeddings. That's the tangent space of the fiber. And well, two of these curves, if I'm allowed to move them, they don't talk to each other. They're completely independent. And I get these two things. And then embeddings, the tangent space of the space of holomorphic embeddings, should have said this is holomorphic embeddings, is going to be the set of holomorphic vector fields on A. So this term is the numerator, this term is the denominator, and that term is the whole quotient. So one thing we see from this is that unlike what happens with Lie groups, this semigroup here does not have the same tangent space at any given point. This tangent space very much depends on what annulus you have. More specifically, if I look at the left translation map, like I fix an annulus and I look at times A as a map from An to An, that map does not induce an isomorphism of tangent spaces. If I'm at the origin, if I'm at the identity annulus, then this thing here is the same thing as that. That's just the diagonal embedding of complexified vector fields on S into two copies of it. And in particular, we see that we get the answer that we want at the identity element. Namely, we just get one copy of this. But at non-identity elements, if A is just an arbitrary annulus, and I look at the map at the level of tangent spaces induced by left multiplication, it's going to send one of these complexified vector fields to the class that vector field comma 0. And you can ask, is that an isomorphism? The answer is no, it's not an isomorphism. Things of the form 0 comma some other vector field, you typically cannot rewrite them in that way unless this vector field admits an analytic continuation to all of A, which usually they don't. So things look a little bit different from the case of Lie groups, and that's going to cause a little bit of a headache. And so it turns out that there's a fix, a sort of, how should I say, something that feels like a little bit random, but actually will do the job. And that goes as follows.
Could you repeat why you can represent everything in pre-image with the same gamma gamma? Sorry.
So I pick an annulus,
Right.
A, and I try to compute this thing. The first thing that I do is I pick an embedding. And then I'm going to write down a formula for this that depends on this embedding. So that's my gamma gamma, gamma in, gamma out. So then you have, essentially you have a manifold down here, which is annuli. You have a thing up there that admits a surjection. I have a point here. I want to compute the tangent space. What do? I pick a point in the pre-image and then compute the tangent space up here, compute the tangent space of the fiber, and say the tangent space here is the quotient of this by that.
Yeah, are you picking a point up above where gamma in equals gamma out?
No, that's A, that's gamma in, gamma out, and that's me being lazy, where I should have written in and out.
Sorry.
No problem. Yes, I can see that being confusing. Yeah, so here's the thing that you can do, which is if I fix an element of the semigroup, an element A, and I define this to be the set of, call them A1, such that there exists A2 where A1, A2 equals A. So if we're working with a group, every element admits, I mean, there's always a solution to that equation. And so this is just a description of the whole group again. But here, because we're in a semigroup, this is not everything. This is only the subset of those analy. So this is A. This is the subset of those analy that can be embedded in here as, so this would be A1, such that there exists an A2 where this whole thing can be written as A1 times A2. Not everything is of that form. Certainly, if you're too long, you can't fit in there. But actually, even for short things, it might be a problem. Yes?
I'm a bit confused that like the cobordism we read as a function from left to right, but here we're composing things from right to left. Is that on purpose?
Well, there's
okay, yes, okay, thank you.
Yeah. There is a way of making it work out, left, right, but so suppose that I want to vary this A1 within that space all the way there. Well, the only thing everything is determined by where this curve here goes. Let's call this curve gamma. Gamma is a map from S into this annulus A, and it completely determines this part. And so what is the tangent space of that manifold over there? It's the set of possible modifications of this curve, which is just a single copy of that. And so that's a way of, if you work with this thing as opposed to the whole thing, then you've somehow magically gotten rid of this annoyance of the fact that the tangent spaces are not all the same. That's going to be handy a bit later on. Okay, so we want to construct some central extensions of this thing. And I have argued that, yeah, so by the way, this allows us to talk about left invariant vector fields. So if I have a Lie group, the corresponding Lie algebra is usually defined as the set of vector fields on the Lie group manifold, which are invariant under left translation. And that's kind of important to have the same tangent space everywhere. Otherwise, it doesn't really make sense to. And so now I have, if I take the whole thing, the tangent spaces vary, and they're just every time a different thing. But here, the tangent spaces do not vary, and moreover, left translation is an isomorphism from the tangent space of this to the tangent space of the identity. And so, because the union of all these, as A varies, is the whole thing, you can talk about left invariant vector fields. They're like vector fields on these that just attach together. So now we have a way of talking about the Lie algebra. To construct central extensions, well, usually the way to go is you first do it at the Lie algebra level, and then you exponentiate to central extensions at the Lie group level. So first, a little bit of Lie algebra cohomology. So the algebra cohomology goes as follows. Let's see, how much do I want to say? So I have G in the algebra, and there's the notion of a two-co-cycle, which is a linear map which is antisymmetric, so omega of xy, so minus omega of yx, and satisfies the co-cycle condition so this is omega of x, y, z, and then cyclic permutations of the symbols x and y, and you add up these three terms, and that should be 0. Given one of these things, one gets a central extension of G, whose underlying vector space is G plus C, and whose Lie bracket is given by, if I have an element XA and an element YB. So A and B are central, meaning that they will not show up in the formula on the right. That's normal. Central things have brackets 0 with everything else. So, and then here we have two terms. The first term is that, and the second term is that. So you can start from this formula and write the conditions that this satisfies the Jacobi and antisymmetry axioms, and you will get exactly the definition of a two-co-cycle. We'll get this. So that new thing is a Lie algebra, which admits a surjective map to G and an inclusion of C, and C is central inside G tilde. Moreover, there's a notion of a two-co-cycle being trivial. Suppose that I had started from a linear functional. So if I have a linear functional mu from G to C, there is a thing you can always do, which is to define omega of xy to be mu of bracket xy. Such things will lead to central extensions that are trivial. They're isomorphic to the direct sum G plus C. The isomorphism is constructed using mu. And so these things are called trivial. And H2 of a Lie algebra, the second Lie algebra cohomology of G, is defined as the collection of all two co-cycles divided by the collection of those which you can write in this form. That's co-cycles minus divided by co-boundaries. And there's a theorem that says that isomorphism classes of central extensions are in bijective correspondence with H2, the algebra cohomology, meaning these divided by these. So now we have a specific Lie algebra, namely the Lie algebra of complexified vector fields on or manifold S. At this point, it becomes convenient to commit to S being the standard circle. I will write So when I write S without anything else, I mean a manifold, which is isomorphic to the circle. When I write S1, I mean the standard circle. That's just a convention that I've been using. In there, we have a basis, standard basis of elements. Consisting of, and this is a standard notation, Ln is by definition minus z to the n plus 1 d by dz. And in that basis, the bracket of vector fields is given by this formula. That Lie algebra is called the Witt algebra. And there is a particular cocycle called the Virasoro cocycle, which is defined in the following way. So if I write it as f of z d by dz and g of z d by dz, that ends up being the standard normalization is 1 over 12, and then integral over S1 of third derivative and then first derivative dz over 2 pi I. And in terms of basis elements for Lm and Ln, it is again the same 1 over 12 m cubed minus m times Kronecker delta between m and minus n. Okay, so the fact that this is a 2 cocycle, namely the fact that it satisfies this particular identity, is an exercise that is not too difficult, especially if you write it in this form. I will not do it here just because there's nothing really to be learned about doing this exercise. The important thing is that the Lie algebra cohomology, the H2 of the Witt algebra with coefficients in the complex numbers, so exactly what I wrote here, so that's the coefficients, turns out to be one-dimensional and generated by this particular cocycle. So this cocycle is non-trivial in cohomology, and moreover, it generates the whole thing. So eraser here.
Sorry, it's a bit stupid. So can one use integration by parts and write down this integral?
I'm sorry?
Can one use integration by parts and write that in more symmetric form in F1G?
Oh, this is, so you can do integration by parts and put one of the primes on the other side, and you get the minus.
Maybe exponential somewhere.
Sorry, this is the formula.
G.
If you had an extra thing. So okay, so if I take a prime and put it on the other side by integration by parts, I get a minus. If I take 2 primes, put them on the other side, I get a plus. If I get all 3 primes, I put them on the other side. So antisymmetry is visible just by integration by parts. Sorry for the mistake. So the Virasoro cycle generates the second Lie algebra cohomology. So I want to give you an idea of how the proof of this goes, because otherwise the formula it's sort of, there's a sort of freedom to set up conformal field theory, like you have this freedom of picking a central extension. I want to sort of tell you where it comes from. It comes from really this computation. So how does one do this? How do you set up this thing? The first thing that you do is there's a lemma that says that, okay, so G is going to be the Lie algebra vector fields on S1, and there's an action of S1 on this Lie algebra, which is given by rigid rotations. And because rigid rotations is generated by an element of the Lie algebra, taking a cocycle and rotating it, there's a lemma that says that this ends up not changing the class in cohomology. So you do that, and once you know that any cocycle is equivalent in cohomology to a rotated version of itself, it's also going to be equivalent to an averaged version of itself, where you average over S1. And so it's enough to look at things that are invariant under S1. A similar argument with mu, if I take mu and then suppose that mu is not rotation invariant, but that d of mu ends up being rotation invariant, then I can average mu over S1 and it will have the same property. And so there's a first lemma that says that this H2 is the same thing as S1 invariant 2 cocycles modulo S1 invariant such one cochains. Okay, so then once you have that, you just go and brute force compute the collection of all S1 invariant supercycles, and it turns out that that space is two-dimensional. And you brute force compute the set of all S1 invariant linear maps, and it turns out that that map is one-dimensional. And then it turns out that the quotient ends up being one-dimensional. So let me tell you what the S1 invariant maps like that are. Well, this is a basis that diagonalizes the action of rotation. And the only one which is invariant is L0. The other ones are not invariant. So an S1 invariant linear functional is going to send L0 to something and all the rest to 0. So there's a basis of this. So there's a basis, and that's given by mu sends Ln to delta n0. That's the only one. This space is one-dimensional. And this one here turns out to be two-dimensional. One of them is L m Ln maps to n cube. And the other one is maps to m. Those are both 2 cocycles. And this one here on the bottom turns out to be the differential of this one here, and therefore that one is trivial. So we're left with this, which somehow people prefer to write it in this particular way because that thing is invariant not just under rotation, but under the group of Möbius transformations. That's a nice property, and so people like that. Write it this way. So how does one go about proving this thing in glue? Well, you first write down the general form of an S1 invariant 2 cocycle. So the general form of an S1 invariant 2 cocycle is S1 invariance means that it's only allowed to take non-zero values when m and n are related by their sum being 0. So n and minus n need to be equal. So we really have a sequence of numbers, one which is the, so you write a general cocycle, S1 invariant 2 cocycle, as Lm Ln maps to C m like that. And then you have a sequence of numbers. So that takes care of the S1 invariance. And then you just write out what this is. That's going to give you a whole bunch of algebraic equations between these numbers. Then it's a matter of doing a bit of algebra to see that once you have the value for n equals, forget 1 and 2, then all the other ones are determined by these equations. You get a highly overdetermined system of equations. You just extract some relations that tell you that. So this space ends up being 2-dimensional, and that's how the computation goes. Really what we want is central extensions not at the Lie algebra level, but central extensions at the Lie group or Lie semi-group level. And there's a general machinery for integrating central extensions of Lie algebras to central extensions of Lie groups. And one can apply this machinery also in the setup where this is not a Lie group, but only a Lie semi-group. And that's where we end up using the fact that there's this trick that we can actually identify some tangent spaces that are the same everywhere so that we can do it. So let me tell you how that goes. So I will write down first the version that's for Lie groups because it's a tiny bit more easy to say. So now I have G, a Lie group, and I'm going to take G to be simply connected. Simply connected, if I took G to not be simply connected and put it through the machine that I'm about to describe, the output would anyways automatically make it simply connected and then also put a central extension on that. So it's easier to start with something which is already simply connected, and then it will just talk about the central extension. And that's something that if you look at here, we have the Z that makes this semi-group simply connected. That's somehow like the first thing that you need to do in order to to start. You first make it simply connected, and then you have a machine that you can apply it to that will produce more. Okay, so I have a simply connected Lie group, and I have a 2 co-cycle from G cross G with values in maybe I shouldn't use A. I was thinking an abelian Lie algebra, but A is a dangerous letter to use because there's analy there. Let me stick to the abelian Lie algebra being the complex numbers. But you could put anything else you want, as long as it's an abelian Lie algebra. Then we're going to define the following thing. So G tilde, which is going to depend on omega, so I'll put here the omega to say that there's a dependence, is going to be the set of pairs gamma comma A, where gamma is a path into G, starting at the identity and ending wherever it wants to end, no condition on where it ends. And A is an element of my abelian Lie algebra. In this case, complex numbers. So the construction that I'm going to make, in case this wasn't there, is just a construction of the universal cover. So I'm going to mod out by paths that are homotopic relative to endpoints. So I say that gamma comma A is equivalent to gamma prime comma A plus a correction. And the correction is going to be integral over some homotopy of omega underline. So let's see. Write all the conditions here. So gamma and gamma prime are 2 paths. They both start at the origin, and they should end at the same point. Then H is a homotopy. So H is a map from 0, 1 cross 0, 1 into G, and that's a homotopy from gamma to gamma prime. Omega underline is the left invariant 2 form, which you obtain by left. So omega is a map like that. That's the tangent space at the origin. So that's what a differential form, a 2 form, assigns at the origin. You can sort of translate them everywhere on the Lie group using left translation, and you get the 2 form that's defined everywhere. That's what I call omega underline. And what do I mean by integrate over H? I mean pull back this 2 form along this map H and integrate on this 2-dimensional manifold. So yeah, it's somehow A remembers where you are in the central extension, and as you go from one path to another path, you're changing where you are in the central extension by an amount which is controlled by this 2 form integrated over the homotopy. So, okay, that's a construction. And then the claim is that this is a central extension of G by the abelian Lie algebra, which is, in this case, C, modulo the periods of omega underline. So here's the thing that can happen. Imagine that this group has non-trivial pi2, non-trivial second homotopy group. That means that it is possible to find a path from a homotopy from gamma, which is the trivial thing, to again the trivial thing, but the homotopy is non-trivial. It's like you like have a little loop that's completely contracted at the origin, and then you open it, and then it becomes big, and then it comes back, and it's again small. And then you've identified an element, which is trivial element, comma, trivial element, to trivial element, comma, trivial element, plus, and now we're integrating over this S2 form. And if that number is non-trivial, then we've done something. We've replaced C, which is by a quotient. So it's important to know whether the group has trivial pi 2. In our case of interest, the semigroup of moduli is actually a homotopy equivalent to S1. It has trivial pi 2, so that story doesn't play any role. And so the only thing that's a little bit tricky is this story of left invariant 2 form. How do you do it if the tangent spaces are all different? Well, you can't do it if the tangent spaces are all different, but there's a trick here. If I replace things by that, then the tangent spaces suddenly are all the same, and I can talk about left invariant 2 forms. So the way you do it is you say, I'm going to be looking at maps that don't land in the whole thing, but maps that land in one of these for a fixed A. And then you can just run the same business and it works. And you get a central extension by the complex numbers. I'm out of time, but there's a thing. I didn't put the complex numbers here. I put C star. And so what's going on? Well, what's going on is that so what we have constructed by this theorem at the very right is a central extension that looks like that. First, you take the universal cover, that's this Z, and then you feed it to this machinery using the Virasoro co-cycle that produces this C. And that is the universal central extension of this in the category of infinite dimensional Lie semigroups.
But still, I mean, sorry, so the 2 co-cycle was only defined on the subgroup, right?
Sorry?
The 2 co-cycle, Virasoro co-cycle was only defined on vector fields.
It is defined at the Lie algebra level.
Subgroup of S1, right?
Subgroup. There's no subgroup. Sorry.
So S1 was bigger than XCS1. Sorry, bigger than the.
Sorry, this.
Yeah.
Yes. What is your question?
Oh, so we did we have a 2 co-cycle actually defined on the tangents? Oh yeah, sorry, yeah. So yeah, I see.
The 2 co-cycle is defined
on the less than A
here via this formula.
Yeah, which gives you a 2 co-cycle on this less than A, right?
We can make a 2 form on this by taking this 2 co-cycle and left translating it. Then we get it on here for every A, we have it on that. And the unit of all these things as A varies is the whole thing. So it's just a way of writing this as a union of things where the tangent spaces of these sub things are now what you want. So then you mod out by a certain element of C. There's a quotient bar from C to C star, given by Z goes to e to the CZ, for C is a given number. That number is the central charge, and that's a parameter. Like a conformal field theory is always a thing that you can only define a conformal field theory of a given central charge. And then it appears in this particular way that it's this particular central extension, namely this, we form it as the push out of this map along this quotient here. So it's a quotient of this, Yeah, so that's that sort of finishes the definition of this thing which appears here. Very good. Any questions?
So why isn't this more like half space instead of the full space? So I'm still a bit confused about the restriction to this less than S.
Yes.
Which is not a subgroup or right? So this is really like there's something like half space or even.
So the union over all A of an less than A is all of an. Sort of for obvious reasons. If I fix a given analysis, I want to know where it is. Well, it's like put this to be equal to that. But that's a union of very, very many submanifolds, and each one of these has different tangent spaces than that. But somehow, in order to, when you define left invariant vector fields, you just put yourself in one of those, and then in there, it makes perfect sense to talk about left invariant vector fields. And then you just say your vector fields, the things that you work with are vector fields on one of these, or collections of vector fields on each one of these.
How does the set part of the central extension work? So is there a unique extension by Z, or is there also some Lie algebra homology that you use the coefficients in Z?
This is not visible at the Lie algebra level. So the universal cover is a thing that I take a group and I look at its universal cover. Locally around the identity element, you don't see any difference. So this is invisible to the Lie algebra. One can ask, how does this trivialization? So I have an element of A. I have an element of this thing, and I get the corresponding trivialization. And now I change this element by an element of the center. You can ask, how does the trivialization change? If I change it by an element of C star, the corresponding trivialization changes by a very specified formula. That very same scalar is used there. How about in Z? If you take an element in Z and ask and modify A tilde by an element in Z and ask how does this change, you will get a collection of scalars, one scalar for every object here, and those scalars are different, so it acts in a way that's sort of not prescribed. Those scalars are called conformal spin. So each element of this has a thing called the conformal spin. It's the scalar that you get by modifying that.
Any more questions?
Do you remember some theorem about these finite dimensional Lie groups not having any pi2?
Indeed, that is a correct statement.
And so you mentioned this thing about, oh, maybe there's a pi2, and I was thinking of that the whole time, but maybe we're working with infinite dimensional Lie groups. Can it happen in that case?
Yes, it can. So a type of Lie group that is very relevant in conformal field theory, and to which we will very soon want to apply this theorem, is the so-called, the eraser is here, or the so-called loop groups. So let me quickly tell you how those are defined. You start with a compact Lie group, compact finite dimensional group G, and then you form LG, which is the set of maps from S1 into G. that's an infinite dimensional group where the group operation is by pointwise multiplication. The Lie algebra is the set of maps from S1 with values in the Lie algebra of this. And there's a cocycle on this, which is given by, if I have two elements like that, f and g. So both f and g are functions on S1 with values in the finite dimensional Lie algebra, which is given by integral over S1 of f dg, and then use an invariant pairing on this Lie algebra to make into. So this Lie algebra with this particular cocycle is something that we're going to use to construct the central extension of that. And if you feed it through this machine, what you end up getting is a central extension where the center, really this thing is not complex. It lives in an abelian real Lie algebra, IR, and then you don't get IR, you get S1 as the kernel, because pi2 of this is non-zero. Pi2 of, so LG is isomorphic as a manifold, not as a group, with base loops times G. This has no pi2, but this you have pi n of base loops of G is isomorphic to pi n plus 1 of G, and pi 3 of G is Z, and so pi 2 of LG is also Z, and this Z here means that I don't get IR, but I get IR modulo the periods, and ends up that it has a genuine effect there. So you're right, in finite dimensions, this does not show up because pi2 is trivial. In infinite dimensions, this does show up in this example. So you integrate this and you're forced to have a certain S1.
All right, so if there are no more questions, then let's start again at 20 past.